We're going to solve exponential equations, and exponential equations are equations that have a variable listed in an exponent, and so we're looking for the value of the variable that makes the equation true. Earlier, we did solve some exponential equations like this very first one, okay? And if you recall, what we did there is that we looked to get the same base on each side of the equation, and we recognized 25 can be written as 5 squared, and so then we decided the two exponents must be equal to each other, and then we could take the further steps and determine that x in this case would have to be 1/3. Okay, so we solved that equation. So now when we compare that to what we have here, since we can't write 7 as 5 to the power, in fact, that's kind of what we're trying to do anyway, isn't it? So we have to have another approach to solving this. Well, it's kind of strange the way we do these is when we were solving logarithmic equations, we massaged the equation and then changed from logarithmic form to exponential form so we could solve. Well, in this case, it's kind of the other way around. We have an exponential equation and we do something so that we end up with logarithms in the equation and we solve from there. Now, the one good thing, here's going to be our first example, okay, our first problem. We're going to solve, of course, solve for x, that's what we've got here. The 5 to the power 3x plus 1 is equal to 7. So we want to know the value of x that makes that true. Now, another thing about these equations, as opposed to solving logarithmic equations, here we won't get any extraneous solutions because powers, unlike logarithms, where we can only take the logarithm of a positive number and we don't want x's that cause the logarithm of a negative number or 0. Here it doesn't matter what an exponent is. An exponent can be positive, negative, 0, so there's no restrictions on what value of exponent can be, and so there's going to be no restrictions in this case on the value of x. So our problem is that the exponent is up in the variable is up in an exponent. So if we can only move that exponent down to a position so that it's not an exponent, and that makes us think about law number 3 of logarithms. So if we had the logarithm of 5 to 3x, see, here's the idea. If we had the logarithm, let's just say natural logarithm, if we had the logarithm of 5 to the power 3x plus 1, then we could actually move that exponent 3x plus 1 down as a factor, and then we'd no longer have to worry about it being an exponent. So what we do, in fact, that idea says, oh, well, let's take the logarithm of both sides. Since the two are equal to each other, their logarithms must be equal to each other. Now, let me also point out, when we do this, we're eventually going to use our calculator. And what two logarithm bases does our calculator have? LOG is one key, which is log base 10. Of course, we don't put the 10 on there, do we? And LN, which is log base E, or natural logarithm. Of course, that's log base E. So since we're eventually going to have to get a number by using our calculator, we're always going to use either log base 10 or log base E when we take a logarithm of both sides. Okay. Well, we proceed now. Because of what we've done, we can bring that exponent down as a factor in front of the logarithm. Now, as we do that, now remember that exponent needs to be put in parentheses, otherwise it would just look like we're multiplying the 1 in the natural log of 5. And I would encourage you to recognize that the natural log of 5 is just an old ugly decimal. I mean, that's what it is. It's an ugly decimal number, and the natural log of 7 is an ugly decimal number. I mean, the natural log of 5 is 2 point something, probably. 2 or 2 point something probably, but it's going to be an ugly decimal. And so rather than putting the decimal in now, we just think about, well, how would we do this? Let me kind of give us a little side information here. if I had 3x plus 1 times 6 is equal to 8. So I just replace natural log of 5 with the number 6 and natural log of 7 with the number 8 and just say, well, now how would we solve that? Well, what would we do? We'd take the 6 and multiply it with a 3x, and we'd take the 6 and multiply it with a 1, and of course that would give us an 18x plus a 6 equal 8. And then next we would subtract the 6 on both sides. And then next, of course, that would be equal to 2, wouldn't it? And then next we'd divide on both sides by that 18, and we'd eventually get 1/9 here. Now that's not what we have, but I'm wanting us to follow that pattern. We have this number, natural log of 5 times the 3x plus 1, so let's multiply that out. And so we would have the 3x times natural log of 5, but it's the 3 and the natural log of 5 that actually get multiplied together. Okay, so let me put this here in this fashion so that we understand that this is the coefficient of x when we do that multiplication. And then plus 1 times the natural log of 5, so we just have that. And then equal natural log of 7. Now, if we compare what we did, remember, this term involves x. This is like an 18x. What we want to do is to get this constant, which is like the 6 we have over there. We want to get this constant to the other side. So we're going to subtract the natural log of 5 from both sides. Now, remember, this 3 times natural log of 5 is like and we can't actually do that subtraction unless we use our calculator. So we're just going to leave it that way. Now, the 3 times the natural log of 5x is kind of like an 18x. If we want to know what x is, then we need to divide out that coefficient. So we'd have the natural log of 7 minus the natural log of 5, whatever that number is, and we're going to divide that by 3 times the natural log of 5. And so this is the exact answer. Okay, this is the exact answer. Now, we'll probably be in our problems asked to not only give the exact answer, but now we're going to approximate and round to 3 decimal places. Round to 3 decimal places, which would be thousandths. Now we got to get our calculator out to do this. And I'll tell you, I'm going to pause here to get the calculator out, but I'm going to go ahead and write down the answer rounded to 3 decimal places. It will be 0.070. Now let me show you how we'll have to enter that in the calculator, because that can be a challenge all its own. That's a complicated thing to enter.
Stop. Well, here I have my calculator. You can see it's a TI-83 Plus. Let me turn it on. Whoops. And clear the screen. And we're to calculate, approximate the value of x there. In this case, it's a fraction, and the numerator of the fraction has more than one term, and so it's critical that we tell the calculator what our whole numerator is. So we'll enclose the numerator in parentheses. So open a parenthesis. Natural log, here's the ln key, as we've discussed. Notice that it opens a parenthesis for my argument, our argument, which is 7, so we have to close the parenthesis on the natural logarithm. Then subtract natural logarithm of 5. Again, it opens a parenthesis for natural logarithm for the 5. We type in the 5 and close the parenthesis. And now we close the parenthesis for the entire numerator. So that represents the numerator. And then we divide. Now we're dividing by 3 times natural log of 5. And if we just type in 3 times natural log of 5, it's going to think we're dividing by 3. And then that result is assuming we're going to be multiplying by the natural log of 5. Anytime we're dividing doing a division and the denominator, what we're dividing by, has operations in it, then it's critical on our calculator to put the denominator, even though it's multiplication, also in parentheses. So open the parenthesis for the denominator, then we'll type in our 3 times natural log of 5 in this case, natural log of 5, so we'll enter our 5, close the parentheses on the natural log of 5, and now I'm closing the parentheses on the denominator. Press enter, and you can see the result, 0.069687, and so on. Now we're to round to thousandths, tens, 100ths, thousandths, the third decimal place. So we look over to the next position, which is a 6, which is 5 or bigger. That means we round up. So this 9 is rounded to a 10 or a 0, and that requires a 6 to be rounded to a 7. And you can see that's what I've done here. Now, it's not unusual that we might think just to leave that as 0.07. Unfortunately, that would appear that we just rounded to do decimal places. So the 0 here is important to indicate that we have rounded to 3 decimal places. Okay, well, let's continue with the lesson now. Let's get started back with that.
Okay, well, that kind of gives us a preview of the way we're going to do these things. Let's move on to a second problem. We have an idea of how we're going to proceed now. We'll do that on the next page. Okay, you see here we're asked to solve one that looks a little more complicated, but we proceed in a similar fashion. Now let's write it here first. Here's our equation. 5 plus 2 times e to the power 2x plus 1 is equal to 115. Now here's a warning. We're not ready to take the logarithm of both sides. We're not ready to do that. If we took the logarithm of both sides right now, we would be stuck. See, if we did this, why would we be stuck? Because we don't know how to deal with the natural logarithm or any logarithm of a sum of things added together. And so on this left side, we couldn't do anything at all. So when the exponential portion, say here, this is the exponential portion. See, there's where that variable exponent stuff lies, okay? When we're given an exponential equation, in most instances, we want to isolate. We want to get that portion by itself. And so in our equation here, the first thing we need to do is get rid of that 5 that's on the left side. And we would do that by subtracting 5 from both sides. And so we would have 2 is equal to e to the power 2x plus 1 is equal to 110. Now, we could go further by dividing on both sides by 2, and that would leave us with e to the power 2x plus 1 alone on the left side, and of course we'd have 110 divided by 2, which is simply 55, isn't it? Now, you might be in a position later on when you're solving, and if you, for instance, if that was 109 divided by 2, we couldn't simplify that nicely. We couldn't reduce that to a whole number. We would just leave it as 109 divided by 2 and proceed from there. We wouldn't do anything further. But this one worked out kind of nicely. Now remember, now we've got the exponential portion isolated. And remember, we're going to take the log of both sides, but we're either going to use log or ln. And typically, it does not matter which one we use. But there is a preference. If we have in our equation 10 to a power, we want to use log. If we have in our equation e to a power, we want to use ln. If we have in our equation 5 to a power, then it doesn't matter. It really doesn't matter ever, but the other two situations that I've indicated there, it's to our advantage to use one logarithm versus another. So here, because I have e to the power, I'm going to say, let's take the natural log of both sides. And when we do that, you're going to see something happen that's convenient. Now, of course, what we did in the last problem, the purpose of that is so we can bring that exponent 2x plus 1 down as a factor. So that would be the next step. But here's the big deal of why we wanted to use natural log, because the natural log of e is what? See, that's like saying logarithm of e base e. And when the argument and the base are the same, we say, what power do I put on the base to get the argument? That's just 1, isn't it? We put the power 1 on an e to get an e. So this value is just 1. And so we have 2x plus 1 times 1, or just 2x plus 1. And you see that makes this much simpler to deal with. So the next thing we would do is we would subtract 1 on both. When we want to solve for x, we'd subtract 1 on both sides. Now let me make a point here. If I put natural log of 55 and then subtract 1, and I get distracted, we know what we're doing, but I get distracted and stop here and come back, and that looks like, oh, that's the natural log of 54. But that's not what it is it? On this side, we have a decimal that's a natural log of 55. And after we calculate that decimal in practice, we're not really going to do that, then we would subtract a 1 from it. And that's not the same as a natural log of 54. So it's a good practice for us to put that argument in parentheses, and we know that that's not going to be subtracted from the 55. Okay, that's a good practice. And so next we would divide out the 2, and so we would have the natural log of 55 minus 1, whatever that decimal is, divided by 2. This is the exact answer. Now, we would have to get out our calculator to approximate it. And so we'll do that right now. And there we have it. Well, let's continue with our examples. I've got probably about 3 more examples I want to do, and they all have a little different twist. So you see here we're solving 5 to the power 3x plus 1 equals 7 to the power 1 minus x, which is, of course, a little different than what we've had because we have 2 different exponents that have a variable in them, and in addition to that, the bases are different. But thankfully, we just have 5 to the power equals 7 to the power. If we had any other features in this, like if we were adding a constant on one side or the other, then we'd have a real hard time solving this. But this isn't so bad. If we take the logarithm of both sides, on both sides we'll be able to take an exponent down, won't we? And it's not going to matter which base we use, but because of our calculator, we're going to use base 10 or base e. Now, I think in my previous examples, I used base e, natural log. This time I think I'll use base 10 just to show you that there's really no difference in the way we approach it. So we'll take the logarithm of each side, base 10 this time. There's no advantage of base 10 over base e or vice versa, because our bases of the exponents are 5 and 7. So there's no real issue about using one base or the other here. Okay. Now, after this step, we can use law 3, and we can write the exponent 3x plus 1 as a factor in front of logarithm of 5. And in a similar fashion, we can bring the exponent down and write it as a factor in front of the logarithm of 7. Now, here's what we're going to do, is we're going to multiply this logarithm of 5 out, and we're going to multiply this logarithm of 7 out. We're going to distribute it. And remember, logarithm of 5 is a number. We just don't know what number. and we're multiplying that with a 3x, so we're really multiplying the 3 and the logarithm of 5. So whatever that product is, that's some number, that's the coefficient of x when we multiply those. And likewise, then, we'll have plus 1 times the logarithm of 5, which would just look like this. Now, over here on the right side, we're going to multiply the logarithm of 7 with a 1, which just gives us a logarithm of 7. And then minus the logarithm of 7 times an x. And remember that logarithm of 7, I don't want to say 7x, that'll look like I'm multiplying the 7 and the x together. To emphasize that that's a number, we're multiplying that times x. Okay, so I'm emphasizing that whole piece is a number rather than putting the parentheses just around the 7. Okay, now, in this case, you know, it's not what we have, but I'm just trying to illustrate the idea. On the left side, we have a number times x, like 4x plus 8. See, we have something times x plus just a number. On the right side, we have some number, log of 7, whatever that is, we'll just say 10, minus some number times x. So we'll say like a, I don't know, just for argument's sake, 2x, okay, just as an example. Okay, I'm just making that up as I go here. But I'm just wanting to show you that we have x's on both sides and constants on both sides. So we would gather everything involving x to one side and everything not involving x to the other. So that would mean we need to add this stuff involving x to both sides. So we'd have 3 times the natural log of 5 times x plus the natural log of 7 times x, okay? And then we're going to subtract this natural log of 5 on both sides, so we'd have the natural log of 7 that's already on the right side minus the natural log of 5. Now, on this left side, that's kind of like over here, we'd have a 4x plus a 2x is equal to a 10 minus 8. Now, when we add the 4x and 2x, what we end up doing is adding the 4 and the 2, and that's the new coefficient times x, isn't it? So in this case, we add the coefficient that's here and the coefficient that here is here, and that's the new coefficient of x. So that would look like, well, 3 times log of 5 plus log of 7. Whatever that number is, that's the new coefficient of x. And on the left side, log of 7 minus log of 5 is just not a number we can calculate in our head, but it's some number, isn't it? And so what we would do next is we would divide out this coefficient. So we'd divide on both sides by 6 in this case and then simplify. Well, here the coefficient of x is all of this, isn't it? So we'd divide on both sides by that long expression. And what we already have on the right side is the log of 7 minus the log of 5. And we're dividing out 3 times the log of 5 plus the log of 7. So this is the exact value. And then we would use our calculator to approximate it. And let's suppose it says round to 3 decimal places, or round to thousands. Round to 3 decimal places. I'm going to get my calculator out privately. I'm just not going to get it up on the screen so that I can give you a value here that you can check to make sure you do it correctly. Well, I've listed over here what comes out on my calculator, and we're to round to 3 decimal places, which would be here, wouldn't it? And so we look at this 6, since that's 5 or bigger, then we round up. And that would change that 9 to a 10, and would change that 4 to a 5, wouldn't it? It changed that 9 to a 0 and that 4 to a 5. And so we would have to put 0.05, 0. We wouldn't normally put that, but we have to put that to indicate that that is what the 3rd decimal place is when we round to 3 decimal places. If we didn't put that, if we put 0.05, it might be misunderstood that we just rounded to 2 decimal places. So the correct answer here, if we're to round to 3 decimal places, is 0.050. Okay. Next page, we'll begin to start ending this lesson. Something I want to do in advance of our actually solving a problem here is I want to do some multiplication because we're going to factor in a moment, and we kind of have to understand what to expect in this factorization. So suppose we have, and I'm just making this up, suppose we have 7 to the x power plus 2 times 7 to the x power minus 4. Okay, let's just imagine that's what we're dealing with. So this is more or less FOIL, isn't it? So let's think what we would do. We'd take this 7 to the x and multiply with this 7 to the x. Okay? 7 to the x times 7 to the x. We'll come back and talk about that in just a moment. And then we take this 7 to the x and multiply with this negative 4. So it would be minus 4 times 7 to the x power. And then we'd take this 2 and multiply with 7 to the x. That's positive, isn't it? So we'd say plus 2 times 7 to the x. And then finally we'd take this positive 2 and multiply with its negative 4, and we'd get negative 8. Okay. Now here's some significance. 7 to the x times 7 to the x. Here we have the same base. I mean, I'm going to compare it. What if we had y to the third times y to the third? What would we do? We'd write that as y to the 6, 3 plus 3. And here the bases are the same, and so we do basically the same thing. This is 7 to the power x plus x. We add those two exponents. But of course, x plus x is 2x. Now, let's go over here. We'll fix that in a moment. What we have in this position, let's look at these two pieces. This is kind of like saying minus 4 times a y plus 2 times a y, if we call 7 to the x a y. And so all we're doing is adding the coefficients there. That would be what? A negative 2y. Well, we have negative 4 of these 7 to the x's and plus 2 of these 7 to the x's. So that's actually minus 2 of these 7 to the x's, isn't it? Minus 8. And so let's rewrite this. We have 7 to the power 2x minus 2 to the power 2 times 7 to the power x and minus and minus 8. And we call this quadratic form, which you studied before in a previous calculus class, algebra class. This is not a quadratic equation, but the significance is the variable portions of this. We look here, one of the exponents is twice as much as the other. See, if we were looking at x squared minus 2 times x to the first minus 8, okay, that is a quadratic form. And that's because the exponent 2 is twice as much as the understood exponent of 1 there. Or x to the fourth minus 2 times x to the second minus 8 is also of quadratic form, okay, because this exponent is twice as much as that. So we have the similarities. Okay. Well, that leads us to this next problem. We're to solve this equation. 5 to the power 2x plus 2 times 5 to the power x minus 3 equals 0. And when we look at this left side of the equation, it looks kind of like the quadratic form we have here. We have a power of 2x in the first position and a power of x in the second position, which we have a 1 power twice as much as the other. And because we saw where this came from, we might try factoring this left-hand side. And so we can imagine that how we would get 5 to the 2x is multiply a 5 to the x times a 5 to the x. That would give us 5 to the 2x. Now, how can we get a minus 3? Well, in one case, we're going to have a minus sign. In the other case, we're going to have a plus sign. And it appears that maybe we would want the minus sign going with a 1 and the plus sign going with a 3, because that would give us 3 times 5 to the x and minus 1 times 5 to the x. And when we add a 3 and a minus 1, we'll get a positive 2, which we need, don't we? So it appears that we have this factored. Now, when we have a product of factors equal to 0, then we set each factor separately to 0, don't we? So we would have 5 to the x power minus 1 equals 0, and 5 to the x power plus 3 equals 0. So we have 2 equations to solve. Each are exponential equations, but relatively simple exponential equations. Okay, these are relatively simple. And so the way we would approach this is we would need to isolate the exponential part. So in this case, we would actually add 1 to both sides, and we would have 5 to the power x equal 1. And then we could take the natural log or the logarithm of both sides, as we have been doing, and that would allow us to bring the exponent down, wouldn't it? Now, if we go further here, let's see, we might as well divide out this natural log of 5 number, so we'd have the natural log of 1 divided by the natural log of 5. Now, if we put that into our calculator, we'll get 0. So we have an exact value of 0 here as a solution. And you could easily check in our original equation that if x is 0, that's going to be true. You could easily check that. But what I'd like to point out first, there are a couple of things in this case. We might have been able to tell what was going on right away here because the natural log of 1 is always 0, isn't it? It's always 0. The logarithm of 1, regardless of the base, is 0. So we might have been able to tell in the very beginning that this is 0 over the natural log of 5, which would have to be 0. Or we might have even been able to tell, we usually can't notice this, but 5 to what power would be 1? Oh, the power would have to be 0. So we might have been able to tell right there that x would have to be 0. But one way or the other, we get a solution of 0, and that's a good solution, okay? Now we've got another equation over here, don't we? 5 to the power x plus 3 equals 0, and if we approach that in the similar way, we would subtract 3 on both sides. And then when we take the natural log of both sides, or the logarithm of both sides, then we would be able to bring that exponent down. And I'm just moving right along here, and then we'd divide out that natural log of 5. And now when we put that into our calculator, it depends on how fancy your calculator is, but you'll either get nonsense, something that you don't understand what it's saying, or you'll get an error message, or you get error. Well, why is that the case? Well, that's because we're telling it to take the logarithm of a negative number, and that's disallowed. Okay, we don't do that. So that's the problem here. So that means that there is no solution to this equation right here. No solution to the equation 5 to the x power plus a 3 equals 0. There's no solution to that equation. There's no x that will make that true. And we could have imagined that because 5 to any power is going to be a positive number. It's either a big positive number, it's a 1, or it's a fraction that's positive. So we just have a number plus 3 equals 0, and that can't happen if that number we're adding to 3 is a positive number. So there's not an x that will make that true, but that doesn't mean there's not a solution to the original equation. We already found that one, and that was x equals 0. Okay, we're going to look at a little different version of this on the next page, one that we have to be rather clever when we see the equation on what to do. Okay, here's our equation, and oh my goodness, this looks completely foreign. Um, this doesn't look like anything we've done before. It looks maybe kind of like the last problem, but not exactly, does it? In the last problem, we had 5 to the 2x plus some number times 5 to the x, and so here we've got a 9 to the x and a 3 to the x plus 1, so it doesn't look similar. Now, let me have you think this way. If we could write this, think of this as something like 3 to the 2x, and then plus some number times 3 to the x and minus 88, then we might have a chance of dealing with that. And then, having said that, maybe that's a big hint, because let me point out to you that 9 to the x power, because 9 can be written as 3 squared, then that's 3 squared to the x power, which would be what? Oh, we would multiply the exponent 2 and the exponent x. That's 3 to the 2x. So we could do that. But that still leaves a problem with what we have here. Unless we notice 3 to the power x plus 1 is the same as 3 to the x times 3 to the 1. See, the same basis, what would we do? We would add the exponents. Of course, 3 to the 1 is just 3, so we could really think of this as 3 times 3 to the x, couldn't we? Now, having done that stuff, let's rewrite our equation here. Replacing 9 with 3 to the power 2x, and replacing 3 to the power x plus 1 with a 3 times 3 to the x minus 88 equals 0, then that looks kind of like what we did a moment ago. So we could certainly imagine trying to factor this left side. So we would have a 3 to the power x times 3 to the power x. That would create 3 to the 2x power. And as we did a moment ago, we'd have to have a plus in one position. I may have done it backwards or different while ago, and a minus in the other. And I mean, there's lots of ways we can get 88, but let me suggest to you an 11 times an 8. And notice, just kind of notice out loud here, when we multiply this, we get a negative 8 times 3 to the x. When we multiply this, we get a positive 11 times 3 to the x. And when we add 11 and a negative 8, we get a 3, which is what we need there, isn't it? So I believe we have it factored correctly. So the next thing we would do is we would set each factor equal to 0. And now I'm going to point out that 3 to the x plus 11 doesn't have a solution, because anytime, we would go through the same thing like we went through a while ago. We would subtract 11 on both sides, and then when we take the logarithm of both sides, we'd have the logarithm of negative 11, which isn't allowed. So this particular equation, and when I say no solution, I'm talking about this equation that we're trying to solve there. That doesn't mean the original equation, this is the original equation, that doesn't mean it doesn't have a solution. Only 3 to the x plus 11 equals 0 has no solution. Now, on the other hand, when we try to solve over here on the right side, we'd add 8 to both sides, and then we would take the logarithm of both sides. And when we do that, of course, the reason is to bring that exponent down as a factor. And then we could, this is just a constant, so we would divide both sides by that constant, okay? And that will make sense. This is the exact solution. And when we use our calculator to approximate it and round to 3 decimal places, we would get 1.893. And so we do, in fact, have a solution to this equation. It's not a whole number, but we do, in fact, have a, natural log of 8 divided by natural log of 3. My bad right up here. I'm sorry about that. Made that error. Okay. So we have exact solution and approximated solution. Well, that is my comments on solving exponential equations. Good luck on your homework.